Okay, to wrap up the Taylor and Maclaurin series discussion, we have one final video here in which we take some of these series that we've known and look at infinite series that are not power series anymore and determine what their values are using the Taylor series that we know. So here are the ones that we've discussed so far. We've got the natural, or 1 over 1 minus x, that's the geometric series, the natural log of 1 plus x, inverse tangent, e to the x, sine of x, cosine of x, and 1 plus x to the k, the last one being the binomial series. Now, in order to prepare us for what we're about to see, I want to make some observations here. First of all, 4 of these have factorials. The last 4 in particular have factorials in them. So when we see an infinite sum with a factorial, we may be dealing with one of these 4. When it's only the odd powers with the factorials, then we might be dealing with the with the sine function. When it's only the even powers, we might be dealing with the cosine function. Well, I'm just going to go ahead and say it. The binomial series is, I don't want to say the ugliest of them all, but it's it's the most complicated of them all. If we see some complicated stuff, it's probably the binomial series. And e to the x is just kind of a nice, hey, I've got powers over their factorials. What about the ones that don't include factorials? Well, the very first one, the geometric series, has only powers of x. It doesn't, we're dividing by anything and that sort of thing. The natural log, we have an alternating series, but so is the inverse tangent. So how do we distinguish the two? The inverse tangent only has the odd powers, and notice we don't have factorials. So those tips can help us as we solve these problems. What we'll do is we'll try to fit each of these to one of those other infinite series. My goal with all of these typically is to write something that is a geometric kind of sequence and then look to see what's around it. Let's look at the first one. I'm going to write this out in full summation form. When n is 0, we end up with, well, 10 to the 0th, 7 to the 0th, and 0 factorial are all 1. That's not terribly exciting. But then we end up with 10 over 7 times 1 factorial. And then 10 squared over 7 squared times 2 factorial. When n is 3, we have 10 cubed over 7 cubed, 3 factorial, and so on. Now, once again, as I said, I like to write one quantity to a power. So let's try this out. We have, well, it looks like the 10s and the 7s are both being raised to a power, so maybe this would be better to write as 1 plus 10 sevenths. And then let's write this as 10 sevenths squared over 2 factorial, and then 10 sevenths cubed over 3 factorial. The next, even though we didn't write it before, is 10 sevenths to the 4th over 4 factorial. And it looks like the sort of variable type thing is the 10 sevenths. If we write this as in terms of x's instead, we end up with 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. And this is the e to the x function. So in our case, our answer is e to the 10 sevenths. Because the radius of convergence for e to the x's Taylor series is all real numbers, well, I guess the radius is infinite, where 10 sevenths fits within that. So this series is precisely e to the 10 sevenths. Let's look at the next one. I've got some alternating business here I can see. What else do I see? Well, I've got 2 factors in each term with the exception of the first term. I've got 1/4 and 1/2, 1/8 and 1/3, 1/16 and 1/4. Okay, I also see that the first factor goes 1/4, 1/8, 1/16, and if I include the 1/2, it goes 1/2, 1/4, 1/8, 1/16. Those are powers of 2. And then I have 1/2, 1/3, 1/4. So let's make these powers of 2 a little bit more obvious. We end up with, let's just do 1/2 minus 1/2 squared Well, okay, I said powers of 2, also powers of 1/2 if we include the numerator. And then that's multiplied by 1/2. And then plus 1/2 cubed times 1/3 minus 1/2 to the 4th times 1/4. And the exponents are matching the denominators. It seems to me that it would be natural to let x be 1/2 and simplify it. And that would give us x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, and so on. We should recognize this from the list on the previous slide as the natural log of 1 plus x. This has a radius of convergence of 1. Well, if my center is 0, which it is, 1/2 is within that radius. And so my final answer is that this stuff is equal to the natural log of 1 plus x, which is 1/2. This is the natural log of 3/2. This third one is actually, to me, the most complicated, and you probably will see why and agree with me as we go here. I see I have 1 over radical 3, and then I have 1 over 3 times 3 radical 3, and 1 over 5 times 9 radical 3, minus 1 over 7 times 27 radical 3. Okay, so I see something strange here. I've got this 3 and the 9 and the 27. Those are all powers of 3. Okay, so we might, and I think this is going to be a little bit incorrect, we might say, well, that's 1 over radical 3 minus, let's see here, 1 over, well, we'll do the 3, and then, well, what about that other radical 3? Let's just leave it like that, and then it's times 1/3, then plus 1/5 times, well, again, what to do with that radical 3, times 1/3 squared, and then minus, I really don't feel good about this, 1/7 times radical 3, 1/3 cubed, blah. That doesn't seem very good. I don't have too many series, and again, that radical 3 in the denominator is kind of puzzling. I don't have too many of these series that go 1, 3, 5, 7, and, well, they do. I do have one, but when it's 5, it should be the 5th power. When it's 7, it should be the 7th power. So maybe that radical 3 is telling us something a little bit more. Well, I do have the arctangent, and I'm going to write it down here. The inverse tangent of x goes x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on. That is the only series I have where I have those odd numbers in the denominator and we're not doing their factorials. So maybe this is the inverse tangent. If that's the case, then the first terms should be equal to each other. So the x and the 1 over radical 3 should be equal, which means that maybe x is 1 over radical 3. Let's think about that. If that's the case, then for the second term, I should have x cubed, right? X cubed over 3. Well, that would be 1 over radical 3 cubed, which, if you need to, multiply it all out. Aha, those first two can be grouped together as 1 over 3 radical 3. Observe that is exactly what we have in that second term, 3 radical 3. And then if I have 5 factors of radical 3, I can pair up 2 of them, which will give me 1 factor of 3, leaving me 3 more factors of radical 3. If I pair up 2 more, that gives me another factor of 3, leaving me only 1 factor. So that looks like 1 over radical 3 to the 5th. Let's write this out just to be clear. So here we have exactly the same thing. 1 over radical 3 cubed turns out to be 1 over 3 radical 3. 2 of those factors would give me 3. 1 would give me the extra radical 3. 2 factors of the 5 would give me 1 factor of 3. 2 more would give me a second factor of 3 to give me 9. And the remaining 5th factor of radical 3 gives me 9 radical 3. And we keep going. So this matches the inverse tangent perfectly, which means this is the inverse tangent of 1 over radical 3. And the inverse tangent of 1 over radical 3, using the triangle over here to the right, is pi over 6. So this infinite sum is, strangely, pi over 6. It's pretty interesting. For our final example, we have a monstrosity. Look at this thing. Oh, okay, so I'm not a big fan of this. It looks pretty awful. I'm looking for my powers, and I see powers of 20, don't I? I've got 20 and 20 squared and 20 cubed and 20 to the 4th and to the 5th. But those are in the denominator, so it's really 1/20th, 1/20th squared. So let's go ahead and pull those out. We have 1 minus 6 times 1/20th plus 6 times, ooh, there's a 2 factorial in there. Let's say 6 times 7 over 2 factorial times 1/20th squared minus 6 times 7 times 8 over 3 factorial times 1/20th cubed. And maybe we'll do just one more here, plus 6 times 7 times 8 times 9 over 4 factorial times 1/20th to the 4th, and so on. It looks like the thing that we're raising to a power is 1/20th, so we'll let x be 1/20th. And I'm going to do something else that's kind of oddball. This is the weird one. This is the binomial series. In the binomial series, that's the only one where we build up having extra factors in the numerator. Now, I've got 1 minus 6 times 1/20th. I'm going to write something down here and then proceed. This is 1 plus negative 6 times x, using x equals 1 over 20. Now, why did I do that? Because the binomial series starts off 1 plus x to the k equals 1 plus kx. So since x was 1/20th, I wanted to make everything else look like k. And then the next term is k times k minus 1 over 2 factorial x squared. Well, I see my x squared, that is this 1/20th squared. I see the 2 factorial, so let's put those in. But it looks to me like k is negative 6. Does that give us a plus? Well, then I'd have negative 6. Negative 6 minus 1 is negative 7. It's working out how I expect it to. In the next term, we would have plus negative 6 times negative 7 times negative 8 over 3 factorial x cubed, and so on. So in our case, k is negative 6, x is 1/20th. Our formula is 1 plus x to the power k. So this is going to be 1 plus 1/20th to the negative 6th power, which would be 21/20ths to the negative 6, or we can take advantage of the exponent. The negative power will say take the reciprocal, and the 6th power we could distribute to both of those factors. So 20th to the 6th, or 20 to the 6th over 21 to the 6th power.